Hello everyone, this is the NPTEL problem solving session for the course Introduction to Algorithms and Analysis. This is week 7 and let's first discuss what were the major topics that were discussed this week. There was a discussion on dynamic programming, on longest common subsequence, on graphs, their definitions, their types, and then prems, algorithm, and graph search. So what we'll do in this session is we'll take up some problems on related to these concepts, and then we'll also discuss theory that will help us better understand those problems and how we solve those problems. And wherever required, I will also just discuss the theory beforehand so that it then becomes much easier to understand the approach for the problems. Okay, so what we'll do is we'll start by a discussion of dynamic programming. So, what is dynamic programming? So, dynamic programming is essentially an algorithm that is used to speed up the overall solution, speed up the search of optimal solution, right? So, when can this speed up the search for optimal solution, right? So, it should have the problem that we are trying to solve. If it has an optimal substructure, right? Right. So what does this term mean, optical substructure? It means that an optimal solution to a problem contains optimal solutions to subproblems. right? So what does that mean exactly? It means that we can look at this statement conversely, that if a problem can be decomposed such that the optimal solution for the entire problem can be written as the optimal solution of the subproblems, right? Then we can try to use dynamic programming, or not just try to use, we can use dynamic programming to speed up the search of the optimal solution for the overall problem, right? So let's, let's discuss this in the context of longest common subsequence, right? Or LCS finding. Right? So how can we use, first of all, what is LCS, and then how can we use dynamic programming to speed up the overall solution for the LCS problem? Right? So what is the LCS problem? Given two sequences, it, where it goes from x1, x2 to xm, and y1, y2 to yn, like so, basically of different size. Find a longest subsequence that is common to both. That is common to both the sequences. Right? Let's call it x. Let's call this y. Let's make the notation also a bit consistent. Right? So let's revisit the example that was there in the lecture notes also, that if x is a, b, c, b, d, a, b, and y is b, d, c, a, b, a, right? So what is the longest common subsequence of x and y? Okay, so for this we can just find it using the brute force uh, LCS algorithm, right? That is exponential. So of course we cannot do that for longer arrays. That's why we are going to look at dynamic programming for the general case. But for this one, right, we can see that if we iterate over x, we find, like, every time we match with y, we start looking for the next index in y, right? Or the index that comes after the previously matched index. Right? So B matches here and A matches here. Right? So the longest common subsequence of x comma y is B A. Right? But this was again the brute force approach, and of course I'll not go through the derivation, but we have seen that in the lectures that brute force LCS finding algorithm is exponential, right? So now how can we leverage dynamic programming for this, right? So uh, if we try to look at the LCS problem, first of all, in the same light as we defined or we gave the definition of dynamic programming, then it means that if Z is the longest common subsequence of X and Y, then any prefix of Z is an longest common subsequence of some prefix of X and some prefix of Y, right? What this means from our example above is that if this is our longest common subsequence, then a prefix of this, let's say the prefix is BC. Now this is the longest common subsequence for a prefix of x and y, right? So this is the longest common subsequence for this prefix of x and y, right? Or we can even say that this is the prefix, right, for the longest common subsequence. So of course, now if we take these three elements, right, the bigger prefix of the optimal or the solution, then this is now a prefix for, like, x has a prefix of this much, right, till the fourth element, and y has a prefix of this much, right? So these are like subarrays or the prefixes of x and y, and the prefix of z is the optimal solution of a combination of prefix of x and y, right? It's not like it's suboptimal or it can have multiple optimal solutions. So this is uh, an example of the optimal substructure that we look for when we want to apply, or when we know we can apply dynamic programming to speed up the solution, right? To speed up the search for the solution, right? And how we achieve this? We write a recursive algorithm for LCS, right? So how that works is we define the LCS over the sequences or arrays that have been passed and the indices in those particular arrays, right? So I is index for x and j is index for y, right? And how we go about it is, if x of I is equal to y of j, then we increase the count of the longest common subsequence, right? So basically, we have found one common character, and we then search for, right? So that increases, right? If these are equal, if we have found a match between x and y, then we increase it to 1, right? So we already have one element in our solution of the longest common subsequence, and then we search. So this is basically 1 plus now the search for the right next elements, right? Or the next elements in ing or in the sequences x and y, right? And if they are not equal, then we again use, or we again define the longest common subsequence as the maximum value or the maximum of these two, right? Of the two trees or the two subtrees of the recursion tree, right? So in one we go to the left in x, and in one we go to the left in y, right? So how does the recursion tree look for this, right? If let's say m equal to 3 and n equal to 4, then we start at the last indices, right? So we start at I equal to 3 and j equal to 4, right? If they are equal, then of course we are going to look for 2 comma 3, right? And if they're not equal, then we are going to look for either 2 comma 4 or 3 comma 3. Okay, and again, like, we keep repeating this until we reach the leaves of the graph, right? So here the graph terminates because we cannot go further than 1, right, index for x, and here we go 1 3, so we terminate this here, and we go 2 2, and then for 2 2 we go 1 2, like whatever. So similar, we can also write it for this 3 comma 2, and then again similar to this. So this subtree, right? So the subtree that is formed here and the subtree that will be formed here, right? They are the same subtrees. So their longest common subsequence, or the size of the longest common subsequence, or like whatever the solution for 2 comma 3 is the same, right, in this recursion tree. Okay, so these are the same subproblems, right? And since these are the same subproblems, right, what we do is, right, or let's say we write the observation that we have, that same subproblem can repeat multiple times in the recursion tree, right? So to speed the overall algorithm up is that what we do is we perform what we call memorization, right? And what effectively is memorization? After computing a solution to a subproblem, we store it in a table, right? And what we do is or at the start of every subproblem, check if it already exists in the table, right? And if it does exist in the table, right, then just it's a constant time table lookup, right? The entire solution of the subproblem. So once you will have to calculate, right? So we'll have to calculate the solution of this problem only once, and all the other times it's a constant time lookup. Else solve, right? And to solve it, we have the we have to like go down the graph, and so that is like of the order of nm or n plus m. For each subproblem, right? But so this is essentially the idea of dynamic programming, that first we identify the optimal substructure, and then we memorize solutions to subproblems, and then look for solution of each subproblem right. We memorize this, or we store the solutions inside a table, and then we look for solution of each subproblem in the table before solving the problem, right? Before essentially performing the recursion for that subproblem. So these are the main ideas that we again use for LCS as well. And after applying these tricks, the LCS algorithm, right, it starts as if the current value of the C matrix for I comma j indices is nil, right? Right. So if it has not been evaluated before, right? If it has been evaluated, then we already have the solution, right? Then we don't need to perform the again like the next steps that I'm going to write. Right? So we check if the table C already has solution for the I comma j subproblem, right? And if it does not have the solution, right, then I perform my usual recursive solution finding for the LCS, right? So then C of I comma j is the LCS, or how we wrote above, 1 plus LCS of x, y, I minus 1 and j minus 1, because we have found the match, right? Else the C of I comma j is max of LCS of x comma y comma shifting x by 1, and we shift y by 1, right? So again, this portion is just our, it's the same as before, it's our usual recursive solution. But what we are doing here is basically we are checking, right? We start by initializing all C I of j with nil values for all I and j, right? And then we check if it has been solved before or not. If it has not been solved before, then its value will be nil. Then we go on to solve it once. And if it has been solved before, the value will not be nil. The value will be what was set as its value the last time it was solved, right? So then we don't need to perform the recursive solution again. We already have the solution for the subproblem, and we just return that. Because this is the dynamic programming solution of the LCS subproblem, or the LCS problem, not subproblem. Okay, so let's take one question. The time complexity of the brute force algorithm used to find the longest common subsequence is a log n. Like, what is the order of the algorithm? Let's see, is it log, is it linear or is it exponential? So we know, like we saw above, that the brute force algorithm is exponential, right? So the best answer that matches out of these four is the exponential, right? Because uh, in long run, the exponential part of it overshadows the contribution of the linear terms, right? So for very large values of n, it will be dominated by the exponential part. So D is correct. Let's take one more problem. Consider the strings PQRS, T, PQRS, and PRA, T, P, B, R, Q, R, P, S. What is the length of the longest common subsequence, right? Between the two of the strings that are given here. So what we can do is, since these strings are fairly small, like we can try to do a brute force search of the longest common subsequence, right? Rather than trying out the dynamic programming based solution, because dynamic programming is like, it's easier when we implement it, right? It's not very fun to write it out. So in the, let's say x is this and our y is p or a t p b or q or p s. So what we can do is, we can start by, since we know that the solution or the LCS of the subproblems of x and y, or the what was the name that we had given to these? The solution of the prefix. Yeah, solution of the prefix of both x and y is a prefix of the final solution. So for brute force algorithm, again, we start by looking at the prefix of both x and y, right? So when we try to do that, we start by matching all these, right? Q, R, S. Right? So these are the values, right, that we get when we match the prefixes, right, or the subsequences or the subsets of both x and y, right? How we did that is we just tried to get the optimal solution for all the sub problems of both x and y, and we kept increasing the size of x and y such that we find the longest sequence or the longest LCS for the smallest subsets of x and y, right? Again, this is a brute force algorithm. It is not very efficient for large values of n, but for small values, we can do this like this, right? So the LCS of x comma y is P R T P Q R S, right? And therefore the cardinality of Z, or the number of elements in Z, is 7, right? So the length that was asked, the length of the longest common subsequence for both these strings is 7. Let's take one more example. In dynamic programming, the technique of storing the previously calculated values is called a saving value property, B storing value property, C memorization, or D mapping, right? So of course we have already discussed this, that the process in which we store the solution of the sub problems, right, in a table, we have called that memorization, right? So this is just like what is the name of the definition, right, or the name of the process that we use. Now I think we should switch gears and discuss about graphs, right, and do some of the problems of graphs, because this week's assignment has questions on graphs. So let's start by writing the definition. So there are two types of graphs, of course, like directed and undirected. So a directed graph, that is also called a digraph, right? Just a directed graph. right? It's defined as a set of vertices and edges, and it is an ordered pair. It consists of, right? It's a set of V and E, and what are V? V is again a set of vertices, right? So it, a graph has multiple vertices or a set of vertices, and set E, right? That is a subset of all the vertices being related together, right? So the edges from this definition, we can see that the edges define a relationship between vertices, right? So they can be either, the relationship can be defined between the complete set, right? Or it can be defined as a subset, right? Usually it's a subset, right? And in directed graph, it is an ordered pair, right? And the second type of graph is undirected graph, right? So it is also a set of vertices and edges, because that's what like a graph is, just a set of vertices and edges where the edges are defined over the set of vertices. The edge set E consists of unordered pair of vertices, right? So what it means is basically, here, let's say if EI is, let's say, VI comma or VJ with VK, right? So this has a different meaning. Let's say this is I1 and this is I2, right? And this is written as VK comma VJ. Then in a directed graph, these two edges are not the same, right? They're different. They depend on the order of the vertices, right, in which they are stored in the graph. While here, in the case of an undirected graph, these are the same, right? So directionality does not matter, or the order of the vertices does not matter, right? But for both these types of directed graphs or undirected graphs, for both, the number of edges is of the order of, like, maximum it can be v squared, like every vertex has a relation with every other vertex, right? So it can be maximum this, and if G, right, if we say that the graph is connected, right? What is a connected graph? So connected, uh, right? So a connected graph is basically where for this set of vertices and edges, there is no vertex that has no connection with any other vertex, right? Or it forms a single graph, right? It forms a single entity, right? And for these kind of graphs, right? For connected graphs, the property that holds is E is either like it's at least the number of vertex minus one, right? And this implies that for a graph to be connected, the order of the edges is of the order of, basically it's a linear order, right? Like in the logarithm space, it's the similar, right? So because if we take log of this, then it becomes O of 2 log v, right, in the right hand side, and this we do not write it usually. But again, this is only for the directed graphs, and this property is what is important. So let's take an example here. Which of the following relation holds for a connected graph with no cycles? The graph has no cycles because the minimum condition, right, that the cardinality of E is equal to the number of vertices minus one, this happens only when there are no cycles in this graph, right? If the cycles are introduced, then the number increases, right? But again, like for a connected graph with no cycles, that property holds true. And basically, that is what the question is. Having V number of vertices and E number of edges, right? So what are the options? That V is 2E, or V is E plus 1, or the number of vertices plus 1 is number of edges minus 1, and D number of vertex is 2 times number of edges minus 1. Right? So again, since we know that there are no cycles, so from the above relation that the number of edges should be equal to the number of vertex minus 1, right? So here E, that is the number of edges, is equal to the number of vertices minus 1, right? So if we rearrange it, we get the second option, right? So I think this I'll cover this much for this week's assignments, and if you have any doubts, you can ask them on the course forum, and I'll stop the meeting here. Thank you.